Hello, welcome to the NPTEL course Fundamentals of Composite and Cellular Materials. The topic for today's lecture is Cellular Solids Applications of Metal Foams. In the last lecture, we discussed the following topics. We discussed about the composite materials designed for stiffness at minimum mass and the design to minimize the thermal distortion. In these lectures or in these two topics, it was basically shown that how the selection of the composites constituents actually can lead to optimum stiffness or minimum thermal distortion in a composite material. The use of the hybrid materials to fill up the holes in material property charts was shown, and in the last part of the last lecture, the advantages, disadvantages and potential applications of composite materials was discussed. This lecture is the first lecture where we study about the cellular solids. The main proportions or main portions covered in this lecture include the basic idea about the metal foams, applications of metal foams for structural, functional and architectural purposes. Now, in this course, the cellular solids will be divided into three different portions: the metal foams or porous metals, porous ceramics and polymer foams or porous polymers. So, the individual topics will be discussed separately. So, in today's lecture, we will learn about the basic applications of metal foams, and in the subsequent one or two lectures, we will learn about the fundamental applications of ceramic foams and or porous ceramics and polymer foams, and that will be followed by the processing of the individual materials or the cellular solids, and then a detailed analysis and description of their fundamental properties and micromechanics and dependence upon the microstructure. So, the main topics or the main keywords that will be covered in this lecture are cellular solids, metal foams, structural applications, lightweight applications, functional applications and architectural applications. So, before we go into the applications of metal foams, the first point or the first question that comes to our mind is what is a cellular solid. So, this diagram was actually introduced in the very second lecture or first lecture of this course. So, this basically shows the various possibilities of dispersion of one phase in another phase. So, as you can see that there can be dispersions of solid, liquid or gas respectively in a gas, liquid or solid, resulting in different combination of materials. So, a foam is ideally defined when a gas is dispersed in a liquid or in a solid, and if the liquid of this gas dispersed liquid is solidified by maintaining the gas phase within the material volume, we actually obtain a solid foam. That means, if we have a molten aluminum with gas bubbles, and then by keeping the gas bubbles inside the metal, if the metal is brought below the melting point of aluminum, so that the aluminum phase solidifies, but the gas bubbles remain inside your material, we actually obtain an aluminum foam. The same goes for also other kinds of foams. But apart from these foams, which are actually technically fabricated by solidifying the liquid between the gas bubbles, the materials or metals having a large amount of porosity can also be fabricated by some other techniques like powder metallurgy techniques using some pore formers or something like that, or also techniques like incomplete sintering. and these will also give rise to some porous metals or materials, and these are also part of this course. That means, this course will cover both the foams and the porous materials. Now, in this lecture, as I have already mentioned, we will discuss about, or we will learn about the basic applications of metal foams, and you will see that these metal foams, because of their extreme properties and combination of properties, they can be used for many applications. So, starting with the structural application. So, the metal foams or cellular solids, as we have already learned, there are few fundamental aspects. The first thing is that the cellular materials have, so the density of cellular materials are very low. So, this is actually the first and foremost thing, that all cellular materials have very low density, because they have a large amount of air. So, the air content or porosity can even be more than 80 to 90%. So, that is why the cellular solids have a large amount of air, and this leads to the very low density of cellular solids. But as we have also learned that although this low density or low or high air content also leads to a low Young's modulus, but when we normalize the Young's modulus with the low density to obtain the specific properties, like for example, E over rho, or for example, the property we learnt in the last lecture, e to the power 0.5 over rho, there actually the cellular solids can actually outperform the bulk materials, and that added with the benefit that they have a low density as such actually makes them very attractive for many applications. Like there are applications where the movable parts in machine components which require sufficient stiffness, at the same time they should be light enough for the easy maneuvering. There actually cellular materials have been used extensively. Such examples are the machine used for drilling, milling, textile, cutting, printing and all other applications, and one such application is being shown in the next slide, where 11 welded AFS parts means aluminum foam sandwich part. That means, this is basically a part where there are two bulk, like these are bulk solid faces interspersed with the foam sandwich part. That means, this is called the foam sandwich part. That means, you have two solid surfaces, and between the solid surfaces are basically the foam region, and these surfaces you will see afterward, these sandwich panels have extremely high stiffness, but they are very light in density. That means, you have seen that the typical examples are being shown over here, where these movable components are used or fabricated using these AFS panels, and that actually leads to a much lower density, but with sufficient stiffness. Further applications of cellular solids like metal foams are found in automobile industries. So, as I have mentioned several times already during this lecture, so whenever a material has low density and high specific properties like high specific strength and high specific stiffness, automobile industry is a very good industry where those materials are actually very much applicable, because automobile industry always looks for lowering the weight of the automobile component, especially if you go for high end automobiles like the sport cars like Ferrari or Porsche or Spider, like in those cars, there even a reduction of a few percent of the weight is extremely important for the end application of the end performance. And in many high end automobiles actually, as we will see in the next slide, these metal foams have been used extensively. Like as you can see over here, these metal foams are often used as for your crash protection, like on the left hand side, or also on the right hand side for this high end automobile. You can see that these door seals are actually made out of your aluminum foam, and that actually serves several purposes. First thing is that because of the use of aluminum foam, the density is actually reduced, and further these aluminum foams are actually excellent material for crash energy absorption. Now, the question is why is such metal forms excellent material for crash energy absorption? So, this is actually can be explained by the compressive stress strain plots. If we compare the compressive stress strain plots of a bulk metal and such metal forms. So, in this plot, so actually I try to draw the compressive stress strain plots in one plot for curves for one plot. For first I draw for bulk aluminum. So, if you can see that bulk aluminum should have a plot something like this or in compression maybe something like that. But a metal foam, they have, you will see afterward when we learn a bit more about the metal forms micromechanics. Metal foams, when they actually are compressed, they actually show a different stress strain behavior. So, first of all they will have a lower Young's modulus, and then they will actually show a very long plateau, and this plateau can actually reach to even 70-80% deformation, and after that they will actually show some kind of a densification, and this densification actually when the opposite cell walls start touching each other and the material gets compressed, and then its Young's modulus actually approaches the Young's modulus of the bulk aluminum or bulk material. So, the basic thing is that now the idea is that why is such a material very good for your crash protection application. So, if now we see for any stress, like for this stress, as you know the area under the stress strain plot is the energy absorbed. Now, if this is our critical stress, so sigma 1 for example, for the bulk aluminum this is the area under the stress strain plot. So, you can see it is only elastic deformation and the amount of energy absorbed is very less, whereas the metal foam, because it starts undergoing the deformation already below the stress, and that means your plateau stress will lead actually such a high amount of area under the curve. So, that means the metal foams can actually be used as sacrificial components. So, they will crush, while crushing they will absorb a significantly high amount of energy, but while doing so they will protect the valuable component of the car and also inhabitants of the car inside the automobile. So, this is the reason that these metal foams are extremely good for crash protection application, and this is often exploited for automobile design for advanced automobiles. Further, these AFS panels or the aluminum foam sandwich panels are also very valuable materials for rail transport industry in many countries like Germany or China. Again, the main fundamental aspects which are exploited are the low density and the excellent specific properties like like high specific stiffness and high specific strength, because again this combination, if you can, the basic idea is that the performance should not be sacrificed while the density should be reduced, and this way we can reduce the weight of the automobile or the weight of the whole car, and that will in end lead to higher velocity and also more fuel economy. So, all these things are actually interrelated, and again some photographs are being shown over here where you can see that these aluminum foams or the metal foams are very often used for such applications which are not actually critical for load bearing applications, but those applications where one can save a lot of weight by actually using these components, not sacrificing the performance, but gaining upon the weight by lowering the density of the component. Also for crash absorption. So, as I already mentioned, I already explained in the previous slides that how metal foams are excellent materials for energy absorption conditions, and then for many applications like there are applications like armor plate applications, and also for many military applications where crash can be a very important thing, like there can be a blast from enemy and then the whole inhabitants in a tank or in any automobile could actually lose their lives if the crash is or the energy is not absorbed properly. In those situations, actually again the metal foams can be designed in such a way that they can actually be used to protect the internals of the automobiles or the military vehicles from the crash energy or the blast energy. So, again one typical this crash protection this component for military applications is shown over here, and again here the primary benefit is that these metal foams, despite providing extremely high amount of energy absorption, they have very low weight, and again low weight is extremely important for military vehicles, because these military vehicles, like in many war type situation, the maneuverability of the tank or the panzer or the military vehicle is extremely important, and then again a lightweight vehicle will add lot of value to the whole scenario, and then again these lightweight metal foams are extremely beneficial for these applications. These were about the structural applications. So, metal foams also find several functional applications. They find applications as sound absorbers, they find applications as thermal materials, they also find applications as filters and so on. So, in this particular slide I show you an open cell foam, and these kind of open cell foams are extremely important for sound absorption applications. So, this open cell, so as you know by now that there is a fundamental difference between an open cell foam and a closed cell foam. What is the difference? Open cell foam contains only the cell edges. So, as you can see from this particular photograph or this particular image over here, these are only the individual edges joined together. There is no material between the edges, and that means there is no face in this, that means the cell faces are missing. You can again imagine, I gave this example at the very beginning, you can imagine the room in which you are sitting. If the walls are all missing and only the corners are there, that means the corner pillars are there and all the walls are missing, you can imagine yourself to be sitting in a open cell foam or an open cell room. That means a house which is being constructed without any walls is a proper example of an open cell structure, whereas now if the walls are all there, the room is properly insulated, you are in a closed cell room, because you have both cell edges and cell faces. Now, this open cell foam is an extremely good or extremely valuable material for sound energy absorption. Why? So, as you can see, because this open cell foam, it actually provides good permeability, because the pores that you have in this open cell foam structure, these are all interconnected. That means, ideally if you enter from one side, and if you are thin enough, or if the medium is thin enough, or it can actually pass through and go out or get out from the other side of the material. This is actually the open cell structure. All the parts are kind of interconnected. At the same time, the path is extremely tortuous. So, what is tortuosity? That means, if a path is something like that, that is not tortuous, but if something like you continuously have to change its direction or something like that, this is the more tortuous path, right. So, now because of this continuous interconnection between the individual edges and continuous, so whenever sound energy is incident on the open cell foam surface, the sound energy actually undergoes multiple reflection and interaction, and by doing that the sound energy actually loses the energy, and this way the open cell foam is an ideal material for sound absorption, and this has been used in very often cases. Again, some examples are being shown over here. So, the figure number A or image A actually shown that there is an audience hall where the ceiling is made out of, there is an opera hall, it's a, and then the ceiling is made out of metal foams, and also the image B is showing one restaurant where you can see the top ceiling is again made up of the metal foams, the porous metals, these open cell foams, and these are excellent materials for energy absorption. So, again you can see here several things have been combined together. One thing is the low density, then is the sound absorption capability, and also this structural stiffness, because they have made the roof of the hall using this metal foam. That means, the specific stiffness of the foam is also one function of one factor over here. Another important factor is that these open cell foams, they have very artistic appearance. That means, if you prepare or if you make these places using these open cell foams, that will also carry some amount of attraction, like visual attraction for the audience or for the customers, for the restaurant, which can also lead to some commercial value. Apart from that, you can also see over here in advanced countries, in western countries, where we have like high speed automobiles, and there actually these open cell foams are often used at the sides of the highways to actually absorb the sound, to actually protect the people who are living surrounding the automobile, surrounding the highway. So, again here the extremely high sound absorbing capacity of open cell foams are used to actually dissipate the high amount of sound from the fast moving automobiles on the highways. Apart from that, these metal foams also have other applications or other functional applications, like as is being shown over here as silencers. So, again silencers use the sound absorption capacity, then mufflers, then diesel particulate filters. Again this is a very important application because you can actually control the pore size. So, you will see afterward that there are many fabrication techniques for these porous materials and the metal foams, and these actually allows you to actually control the pore size or the pore size distribution, and this way you can also use them as various filters or catalytic converters. So, again these will be shown in the future lectures. Now, one very important application for metal foams is as heat exchanger materials. So, as you can see over here, these heat exchangers are extremely important for many modern applications, like typically for electronic components or also for many also in many other functions. And for heat exchanger applications, you need some fundamental properties. One thing is that the material should have a high surface area, because a high surface area gives you good and then you also, the material should also have like property like high thermal conductivity, and also a good permeability is also a very important factor. And combining all these components like porous copper, like porous copper heat exchanger or copper foam heat exchangers, they have become very popular these days for many advanced applications. Also in this slide, this is being shown like this is a powerful LED lamps, like again in these components also, because these are extremely high energy density component. So, here the amount of high energy which is being generated because of the very high amount of power. So, if this energy is not immediately dissipated, that can actually lead to the failure of the whole component, and that would be very expensive, because these components are not economic, they are not cheap, they are quite expensive components. So, again for the protection of these things, you can see that these continuous metal foams or these open cell foams, they actually provide a very high surface area, and then if the material also has a high conductivity, then one can use them as very good these heat exchanger materials to provide actually good life to these components. Apart from that, metal foams have also other applications, like especially for biomedical applications like titanium foams. As we all know, this titanium is a very special material, because titanium has many attractive properties, like it has got good mechanical properties, it has got sufficient corrosion resistance, and it has also got good biocompatibility, and it is also osteoconductive. That means it actually allows the bone tissues to grow around it. That means if a titanium is made, or titanium is made to form a formed titanium, and this formed titanium or titanium foam can actually be used for bone scaffold or for bone implant applications, for many biomedical applications. And apart from that, titanium also has other properties, like it is very good, it has very good fatigue resistance, it has got good fracture toughness, and also in vitro stability. So, some applications where titanium foams have been used for biomedical applications are being shown in this slide over here. Also, this is another application where some titanium foams have been used for also some biomedical applications from Apart from that, as I already mentioned, so metal foams also apart from all these many whatever properties I mentioned, metal forms also possess excellent aesthetic applications, like as you can see that in many places these metal forms are used for to draw the tourists, for example, like they actually provide many, like one, I mean they are very unique appearance of these metal forms, and this can again be used for many functions. So, overall I have shown in this particular lecture that metal forms have many applications, but again the kind of application actually again depends upon the type of porosity we have, and also like what kind of applications, like if the application is intended for structural applications, like as we mentioned, like for automobile applications, for aerospace applications, typically for energy absorption or load bearing components, in those applications actually a closed cell foam where you have both the cell edges and the cell faces, they are actually more appropriate. That means, the closed cell foam with reasonably high density are actually more appropriate for structural applications, whereas for more functional applications like heat exchangers, filters, sound absorptions, for foam, for biomedical applications, for all those applications actually an open cell foam with more controllable porosity is actually more intended. That means, again the structure of the metal foam should actually be controlled to obtain the properties which is actually or which are actually intended for the end application. So, overall in this lecture we have covered the basic applications of metal foams. So, we have learned that metal foams are dispersions of gaseous phase within a metal or alloy, but there can also be porous metals which are not metal forms strictly, because porous metals are not fabricated by kind of solidifying the liquid, but rather by introducing some pores in metals by some powder metallurgy route. But all in all, these porous metals or metal forms are extremely important for many applications. They have many structural and functional applications, and depending upon the applications, the foams are either used as either open cell foams where a high porosity for more functional applications, or closed cell foams where a more closed porosity and for more structural applications, mainly as energy absorbers. So, the references for this lecture are given here, and in the next lecture we will cover the applications of polymer foams and also ceramic foams. Thank you very much.